speak about maximizing alternative fuels and also making a link a little bit with CO2 emissions. That will be the next webinar in September. So it's a good link there. My name is Maia. I'm responsible for European and African operations of FCT Combustion. We have a lot of slides here, so you should get a copy of these later on. So I'll just jump through some of these slides and you can look more in details later when you get a PDF copy from Thomas. A little bit about the company, very briefly. FCT has three main branches. We are working three main branches. One would be FCT Combustion, that is responsible for all the combustion equipment and processes that we have in our company, including what we are speaking today. One is FCT Tech, supplying online analysis mainly for process control. So you can have this equipment for a fast evaluation of free lime or clinker components or cement composition. And FCT flames, that we are making mostly entertainment flames for Olympic Games, for example. We are working in different industries. Our main industry is cement, but we are also in iron ore, lime, pulp and paper, mining, other types of mineral processing. For example, lithium is a very hot topic for us these days, mainly because of the electro batteries. And a good point of being in many different industries is that you can bring technologies from one industry that are very well known in one industry, you can bring to another industry. And this has happened already with us from another industries to cement and vice versa. FCT started as a burner suppliers almost 40 years ago, but today we are able to help our clients in different areas. Here is just a sketch of a cement plant and which areas we are able to help you. And here, for example, just some random pictures of our projects. So hot gas generators for gas and oil, hot gas generators for 100% alternative fuel, kiln burners for high substitution rate, control panels. These are burners and valve trains for iron ore pelletizing here, a calcined clay, flash calcination plant that we are able to supply, and so on. We have 5 main offices. Our headquarters are in Australia. We have also an office in China, one in Brazil, USA, and this one in Austria, responsible for Europe and Africa, where I'm sitting at the moment. Apart from that, we have several agents in different countries, and our main idea is to be as close as possible to our clients. Here in this slide, you can see some of our clients, again, in different industries. You can see the major cement players over there as well. And after this, so here I stop talking about the company and I start talking a little bit about alternative fuels. First of all, a little bit about the combustion. So when we are trying to burn a particle, there are different stages that this particle has to go through before it's completely burned. The first stage would be a drying phase. So the fuels that we are using, specifically alternative fuels, they have a certain moisture, in some cases 5%, some cases 35%, and they have to go through a process of drying, first of all. After the drying is completed, the particle starts to release the volatiles, which are the easier parts to burn. And in the case of some fuels, they have a lot of volatile. For example, RDF is 65, 70, 75% volatiles. In other types of fuel, you have less volatiles. But this is a common stage of the combustion. After that, after all your volatiles are consumed, you start burning the char, so the fixed carbon that is remaining in your fuel, and then at the end you have the ashes, right? That in a case of a cement process, it will be incorporated into the clinker, mostly into the clinker. However, this explains the combustion of each particle isolated by itself. So if you have one particle of RDF in suspension with a lot of oxygen around it, this is how it would happen. But we all know that this is not what is happening inside a clinker kiln. So in a clinker kiln, if we take a flame, I hope you can see my mouse. If we take this sketch of a flame here, and we take these 3 cross sections in different lengths away from the burner, we can see that close to the burner, we have a very high number of particles, a high number of RDF, because this alternative fuel, because this didn't start burning yet. And these particles, this large number of particles, they are all close together. So they didn't have time to spread across the kiln. If you take at the end of the flame, most of the fuel was already burned, so you have a small number of particles, and they are very far away from each other because you had enough time to disperse them into the kiln. And then if you take a certain intermediate position, we have two situations. So on the periphery of the flame, you have a large number of particles very well dispersed, and in the center of the flame, you have also a large number of particles, but they don't have a very good dispersion. Depending on how many particles you have in a certain area and how dispersed they are, how well in contact with oxygen they are, they will go through a different combustion behavior. And I have to say that in a flame, as we can see here, you can see all these 4 different mechanisms at the same time. Some areas you have more mechanism 1, some areas more mechanism 2, but all 4 mechanisms are happening at the same time. Here is just a diagram to show on the vertical side, we have the number of the particles that are in our flame and going from low to high, and how dispersed these particles are going from low on the left, high on the right. And here are the 4 different regions. And what we do is we start here with a very high number of particles with a very low dispersion. And as the time goes by, they are getting more and more dispersed, and they are getting more and more burned. So the number decreases and the dispersion increases. With the design of the combustion equipment, you can change how the flame goes from this point to this point. So the beginning and the end will be the same, but how the flame is going from this point to this point, you can interfere with the burner design. If we try to understand a little bit what happened in these 5 regions, we can see that in this region where the particles are all together, basically what happens is that the particles, this here would be a cross-section, a sector of a cross-section of the flame. So if I go back, if you would take a cross-section of the flame, this circle here, and make a sector of it, this would be a diagram of it. So basically, the particles that are more outside the fuel cloud, they would start releasing the volatiles, and these volatiles would burn outside the flame. Then, if we go to region number 2, the particles are a little bit more dispersed, or we have less particles. What happens is that this outside layer is continues to supply to supply the volatiles to be burned outside, and the inner side, that before here, the black part, starts also to release volatiles, and these volatiles also start to go out into the flame. Then the next phase, region 3, the particles outside, they consumed completely the volatiles that they had. The center is still supplying volatiles to this area, and the particles that started burning here at the beginning, they already completed all the volatile combustion, and now they start burning the char, as we saw in the previous slide. And at the end, so if we look at the end of the flame, so every volatile is already burned. We only have the char, and then each particle is burning individually, the char part mainly, and this is basically the end of the combustion. This mechanism is happening for every type of solid fuel, or liquid fuels as well, but mostly solid fuels, and independently if this is an alternative fuel or coal, for example. Another point that we should pay attention in terms of theory, how to fire alternative fuels, would be the importance of the aerodynamic of the fuel. So there are different fuels in different formats, and some of these will fly better than others. And to evaluate how well a fuel is flying, there's a number called sphericity. Basically, you take the area of the particle and you put below, and you you take a sphere with the same volume of your original particle and put on the top, the area of this. I have some examples here. We have 3 different fuels: CO2 sludge, wood chips, and fluff, RDF. But let's consider for now that these 3 are the same material, the plastics, for example, in different forms. Here you would have the dimensions of this fuel. So here would be, we are simplifying obviously, but here would be spheres of 6.2 millimeter diameter. Here would chips, plastic chips in this case, fictively, would be 8 millimeters by 4 by 4, and the RDF particles 25 by 25 by 0.2. So what is important to see here is that the particles, they have the same volume, all of them, if we consider these measurements here. But you can see the surface area is, in the RDF, for example, is 10 times larger than the grains from CO2 sludge. This means that the particles, as we saw in the previous slides, they are burning on the outside first. So these particles of RDF, they have a much better chance. They burn much faster than a sphere because they have much higher surface area. And what we want to see here is this sphericity number. So obviously the CO2 sludge, the sphericity is number 1 because it is a sphere. And then when you go away from this sphere form, like for the RDF here, you see that the sphericity is very low. So low numbers mean that this particle will fly easier and it will have more contact with oxygen in the surface. Here, just 3 different videos to show the shape of the particles, how this influences. So we have here a thin 2D plastic particle like RDF. So you can see the combustion is already finished. Here you have a very thick plastic material, and here you have a 3D as well wood particle, and you can see how the ignition changes between these 3 different shapes, how fast they burn completely, and how is the behavior of the particle during the combustion. Yeah, so here we would have a very low sphericity, and here we would have a very high sphericity. So if I play this again very quickly, you can see that here it started very fast and it's already formed some droplets and it's finished. Here this particle is curling around itself, forming a sphere more or less, and then it's also finished soon. And here this is a very stable material, doesn't change the form, so it will stay there for a long time, as you can see here. We don't have time to see the whole video, but you get the point. Now, obviously, we are talking about alternative fuels, but our clinker kilns are not producing, incinerators, so they are used to produce a product of clinker. So we have to take in consideration as well, when we are talking about combustion of alternative fuels in a clinker kiln, the mineralogy of the clinker. So here you can see a diagram that all of you are for sure familiar with the 4 main components. And what is important to say here is that there are 2 different phases. One phase where you are preparing the clinker, so you start with the final drying, then you preheat the material, you start calcining it, and then you come to the transition zone. And then a second phase where in this phase you have a very strong, what you are doing in this phase has a very strong influence in the clinker quality. So we have to differentiate these 2 parts because this will influence how we can burn alternative fuel in the preparation phase and how we can burn alternative fuel in the clinkerization phase. Here, just a diagram with some different possibilities of lines for drying, preheating, calcining, and clinkering. With the different technologies from the past. And if we are talking about a modern line today, we would have some cyclone tower for preheating, we would have a calciner for the calcination part, we would have a short kiln for the clinkerization, and then a very modern, efficient clinker cooler, grate cooler for the cooling part. And when we put our diagram back again into this different above here to compare, so this section of the process would happen in the preheater, and so on and so on. And here you can see more or less the time that the clinker or the raw material is passing through each phase. And what is important to say, as I told before, we have to differentiate between the preparation phase and the clinkerization. In the preparation phase, what is important is just a controllable input of material, of alternative fuel, and that the calciner itself and the injection points and so on are, allow the release of energy inside the calciner itself. We don't want fuel going out of the calciner, burning the preheater tower, or coming inside the kiln inlet, and so on. And then at the kiln, obviously, as I said, this part of the chart, has a very strong influence in the quality of the product. So we require a very narrow and short flame to produce a high quality clinker. So we need that the fuel releases its energy in a certain specific way where we want it to be. So basically, there are two different types. So when we are trying to inject alternative fuel in the calciner, is like when you are trying to choose a house to buy. So when you want to buy a house, you are the main concern. One of the main concerns is location. Where is the house? How is the neighborhood? How is the atmosphere around? Which possibilities of transport you have near your house, and so on. And to inject alternative fuel in the calciner is very similar. It's again about location. So you should search for areas with higher temperatures, with higher oxygen content. You should look into the velocity profile inside this calciner, check the residence time, and so on. And now when we talk the same about the kiln is another story. In the kiln, it's like we are choosing to buy a sports car. I'm sure all of you have one of these at home. So when you choose one of these cars, for you, the most important point is the performance. How much power this car has, how fast can it go, how efficiently it can turn, and so on. And for the main burner, for the kiln, is the same. So how much alternative fuel you can use, how efficient is the mixing of the fuels with oxygen, how much you can control the direction of the particles, and so on. And then there are also other points that I will not discuss in details here, but obviously the ashes of the fuel have influence. So if we look into this diagram, silica, calcium, and alumina, and iron, we can see clinker is down here, so very high in calcium and silicium, aluminum, and we can see, for example, plastics and rubber, they are very far away. So there's a difference between the ashes of the fuels, in this case alternative fuels, to the clinker. And also if we are talking about, for example, tires, so you can see. So there is an influence. I will not discuss here in detail, but you can see that these four main components that we have in this chart are also in the modules of the clinker, so they're very important there. It's something that should be considered, but not for today. Also, another point that it's very important, but it will not be discussed very much, is the sulfur cycle. So we are inputting some sulfur. Most of the case, we're inputting some sulfur with the alternative fuels. Part of this will live with the clinker, hopefully, if the chemical composition of the clinker is correct and the burner is doing a good job, and part will really leave the kiln as exhaust gases. And another one is the chlorine cycle, similar case. In this case, the burner, it's almost nothing will leave through the clinker, independently of how the chemistry of the burner is. You need to have a chlorine bypass. Now, coming to more practical cases, as I said, to inject, the easy part is to inject in the calciner, alternative fuel in the calciner. So if you have a calciner and you want to start burning alternative fuel, you should start there. One way to choose the correct point, the correct location, would be using CFD. So you can see the difference between right and left here. Here you still have unburned particles coming down the calciner. Here they were all finished, and the same here, the mixing with the gases and so on. CFD could also be used for the kiln burners, but it's not the main tool. This is only to correct some specific problems, like in this case here, where you could see that the alternative fuel particles were flying outside the flame, and you can see that the CFD replicated the same. And then you looking into this, you can find solutions for very specific problems, but this is not the main tool for the kiln burner. And then obviously when we are using alternative fuels and we have a poor performance of the equipment, we all know a lot of clinker quality operational problems can happen. We can see brown clinker, white clinker that's not white anymore, and so on. So when we're talking about alternative fuels in the kiln, there are different areas. So we have around the burner secondary air with a very high oxygen amount, but we don't control this, and we don't control the direction and the mixing of this as well. Not. And we have another area, the primary air inside the flame, where we have a lower oxygen availability, but we have a very high control and mixing capability there. When we look to this diagram, there would be three main possibilities to inject this alternative fuel through the kiln. So option number one would be using putting directly in the secondary air, and option number two just above the burner, and option number three directly through the burner. When we look to option number one, would be a satellite kiln like this. In this area, we have a very the highest oxygen availability of all three. But we have a very low control and a very low mixing. When we are talking about these pipes above the burner, these were used in the past mainly. We have a higher oxygen, lower oxygen than in the satellite burner, but higher than through the burner. But we have a little bit more control and a little bit more mixing. And when we are talking about a modern burner used these days, we have a very low oxygen, because in the center of the flame we have lower oxygen than in other two cases, but we have a very high control and a very high mixing. Speaking firstly about the option number one, the satellite burner, it would be a miniature burner, if you will. Basically, it's a pipe. In this pipe, we can adjust the angle penetration to influence the flight path of the alternative fuel. We would have some refractory lining around to increase the lifetime of this equipment, and we would have additional air to increase the control that we have over the particles. Advantages of the satellite burner is that you inject this a little bit behind the burner itself. So between this region where you inject the alternative fuel and the flame itself, you would have a pre-drying effect, also a preheating of the particles. It's very easy to install, so only minor modifications are required. In case you want to start the kiln, this is ideal for that, so it's a very easy solution. But there's a limitation in the maximum substitution rate that you can use. Obviously, you can understand that in a burner, you have the flame very nicely centralized. And now, using the satellite burner, you start removing fuel from the center of the kiln and putting fuel somewhere outside the center of the kiln. So you cannot go 100% fuel in this direction, right? So otherwise, you would have problems. And then when we are talking now, option number two, I will not talk. This was an old solution. These days is not used anymore. But when I'm talking about option number three, a modern kiln burner, we in FCT started years ago to study the influence of the air distribution in the burner, how this would influence the combustion of the RDF, the alternative fuels. So as I mentioned, we have a CFD group inside our company, doing CFD for clients and also for our own research and development. And we came up with a standard burner design with axial air, coal, and swirl air, alternative fuels in the middle. And then we raised the question, what would happen if here we would have 36 holes, we keep the same area, same amount of air, everything, we just inject them through 18 holes a little bit bigger. And the next question would be, what happens if we take these 18 holes and just put them together like that, creating a space in between. Okay, we did that in our CFD. So we replicated the flame inside the kiln for these three different situations. Here would be with the 36 holes. We can see here in this chart the peak radiation of the flame and also the energy released in the clinkerization zone. So we can see when we go to from 36 holes to 18 holes, we can see the peak radiation increases and the flame gets a little bit shorter. And when we put them together 3 by 3, we can see that the peak radiation increases even more. So it's a more intense flame, and the flame got, again, a little bit shorter. So from one point of view, if we have the black line here, we would have a very milder flame, not so intense, and with the good for generating less NOx, for example. But in case we want to maximize our alternative fuel, we want to have a very radiative flame, a very intense flame that can burn properly the alternative fuels that are harder to burn. So it's hard. Then we thought, how could we do to have the two situations in one burner? And this is what we did. So we have a burner that has axial air divided in 2 channels. So the blue orifices would be supplied by a certain part of the axial air, and the red ones by another part, and they are just controlled with one valve. You open or close this valve. So if you open the valve, you have all holes blue and red in operation. If you close this valve, you have only the red holes in operation. Basically, what you can have is 2 modes of operation with the same burner. When you have the standard mode, meaning all holes in operation, you would have a situation like this. And when you have the boost mode, only with the 18 holes, obviously there's a little bit of air coming out here just for cooling and avoid blockages. You would have a much higher performance of the burner. Not only in terms of velocities here, meaning higher momentum, but also you create space between these high velocity jets, and this space is perfect for sucking secondary air, which has the most oxygen in the kiln, into the flame. To check about the secondary air, we made a cross-section in the kiln showing only the secondary air lines. Here would be in the standard mode, how much air you are sucking inside the flame. And here with the boost mode, you can see that you suck much more oxygen into the flame from the secondary air. It's a hot and high oxygen content air. Again, the same curve, just to illustrate again. Boost mode, we would go much higher in the peak radiation, and also the flame would get shorter. And this is also the same for different types of fuel. So here with 50% RDF, for example, obviously we have different peaks. So for coal, one for the RDF, but when you go to boost mode, these 2 peaks, first of all, they go up. So you are burning the RDF much better. The RDF goes back closer to the burner, and the 2 peaks, they come closer together. So you don't have this colder flame in between them. Again, you have one burner with 2 possibility to operate. If you have the boost mode, you can use a high alternative fuel substitution. And if you are with low amount of alternative fuel, you go back to standard mode, and then you can have a much easier flame, but a flame that is more producing less NOx, for example. And these burners, they have also additional features. For example, you can see here there are holes inside the alternative fuel pipe divided in the green lines and the pink lines. You can see them here in the picture. And basically what we are doing, we can control these 2 separately. So in case we have a very heavy fuel that tends to fall 3D particles, for example, we would use only the green lines to lift these particles and keep them in suspension for a long time. Or if you have a very light fuel, easy to burn, like RDF, for example, we would open both the green and the pink lines, and then we would have a dispersion in all directions symmetrically in the flame. And another feature would be, for example, wear protection. So inside the alternative fuel pipes, we can have some special material inside to minimize wear. Here we can see, last slide, we can see two flames, one in the left with, both are with 80% alternative fuel, but you can see that the one in the left is a little bit better. In the right here, you can see some material falling onto the clinker and burning close to the walls and so on. You can see a much shorter ignition on the left side than on the right side and so on. Both kilns are running with 8% alternative fuel, RDF in both cases, and the remaining being petcoke in both cases, but the flame on the left is much more optimized than the flame on the right. I just wanted to show this to say that there is 80% and there is 80%. And today we are even operating burners with 90% and really 90% of hard to burn alternative fuels like RDF, for example, not solvents or something like that. And to complement about CO2 reduction, I think there are other points that we don't have time for discussing today, like hydrogen, to replace carbon-based fuels by hydrogen. I think there's a lot of movement in that direction, and we as FCT, we are working hard on this with clients already making tests. Calcined clay, we as well, we can, I don't know how familiar you are, but we can replace part of the clinker by calcined clay, and calcined clay has virtually no CO2, so you don't have limestone. You basically have a aluminum and silica compound, and this after treated, heat treated, can behave similarly to clinker. And obviously, you can also improve efficiency on the burners themselves and in the process, and this will save your fuel independently which type of fuel you're using, and this in turn will also improve the CO2 emissions. We are working all of these areas and others, so please, you can check our website and you can see more details there. This was my presentation. Sorry for running around. A lot to cover. I hope you could understand. And if not, you get a copy of this presentation. And if not, please contact me anytime. You'll see my email in the first page of the presentation, and I'll come back to you with some more information and answers. Thank you very much.
Thank you, Joel. That's a really comprehensive presentation, looking at the theories and concepts behind combustion, and then a great overview of calciners and burners. So thanks for that. There's quite a few questions in the Q&A. I'll just pick a couple and then maybe you can finish off afterwards. But you mentioned it's easier to start in the calciner, and just on that note, what kind of split between the calciner and the main burner do you typically see in the installations that you visit?
No, this depends a lot. So this can go, some plants they have no calciner, right? So 0, and some plants they have very efficient calciners that 60-65%. So the point that I raised, why it's easier to go for the calciner first is that the calciner is in this first phase, as I mentioned, the preparation phase. So how the alternative fuel is being, as long as the alternative fuel is being burned, doesn't matter how, it's not exactly like this, but it has a less importance how, as long as this fuel is burning and releasing the heat, the energy to calcine the material, this is enough. So it's much easier than putting in the kiln burner that we have to control much better the combustion conditions, for example. That's why.
And what kind of burner is used typically in the calciner?
It depends a lot on the type of calciner. I think new calciners, they are designed already for alternative fuel. They have a much longer residence time. So in that case, you don't even need a burner. A simple pipe would do the job. But in other cases, a burner could be beneficial if you have an old calciner and you want to inject there some alternative fuels and you don't have enough residence time. So then a small burner would be similar to the main burner, but in a smaller scale, a bit simpler. Would bring you some benefits because it would allow you to have a better mixing, a better control about where the alternative fuel is going in the calciner. So this would buy you, let's say, some extra time for combustion.
Okay. Just about the actual main burner, can you talk a little bit about your experiences with hydrogen? Is that as a kind of accelerator, as a support for burning alternative fuels, or are you looking at hydrogen as the primary fuel?
Both things. So first of all, hydrogen has been used already for many years, in very tiny quantities, very small quantities. The same with oxygen. So oxygen is also being used for many years in a very low quantity. In both cases, until now at least, the main idea was to improve the combustion of the other fuels. So you would put a very low amount just to improve the combustion of the alternative fuels, for example, of both hydrogen and oxygen. But what we are seeing more and more is that obviously hydrogen doesn't have carbon in its structure, and this could be a way to go in direction to decarbonization. For cement production, for clinker production, there are some obstacles and some barriers that can be partially overcome. We wrote an article about this, going details about which influences hydrogen would have in the clinker process. It's in our website, we can find it there. Yes, so two different points. One is a small amount of hydrogen for improving combustion of other fuels. This is used for many years and it's available technology. And another one would be a high substitution by hydrogen, talking about 50–60%. Problem with this is today hydrogen is still either very expensive to be produced, or it's produced from not from a environmentally friendly situation. For example, most of the hydrogen produced today is coming from natural gas. So in that case, due to the efficiencies in the process, it's better if you burn the natural gas directly instead of making hydrogen and then using it.
Sure. Yeah. No, an interesting area. There's a few studies that have been created on hydrogen, well worth looking at. But like you said, the grey, green, and blue hydrogen, the different types. Some of them are not readily available, and
this was this discussion that we had in this article. So exactly that. Yeah.
Okay, well, thank you very much, Joel. It's so much to talk about. There are lots of questions for you in the Q&A. Please have a look. We don't have time now to address them all. We're going to have to move now to our next speaker, but